Let's imagine again that we've got some object and we have some force acting on it, some force in a general direction. I'll call this the force vector F. And we've got some displacement. So here's our displacement. I'll call that the displacement delta R. But for the moment, let's imagine, or let's define, our x-axis as along our displacement. So let's imagine that whatever the direction of the displacement, that's we're going to define as our x direction. So we can think of this as delta x. Now, because I'm only going to be using the magnitudes of the displacement and the force, let's not worry about these at the moment. Okay? Now, what is the work? The work is F delta x cos theta. And again, I want to think about this F cos theta. What is F cos theta? It's the component of the force in the x direction. So what is that? That's F sub x, the component of the force along x. So our F delta R cos theta, we can now write as F delta x cos theta, and the F cos theta we can write as F sub x delta x. So just by defining our displacement in the x direction, we can write the work done as the x component of the force times the delta x. Now let's make an assumption. Let's assume that this force that we're talking about, this force is not just any old force acting on the object, but the net force. Let's assume that this is the net force acting on our object, the total sum of all of the forces acting on the object. So we're going to make the assumption that F of n equals the total force. We could determine the work done by any of the forces acting on the object, but now let's imagine that we are determining the work done on the object by the net force, so only the total force. What do we get in that case? Well, let's come down here, and I'm going to rewrite this as F sub x, and rather than delta x, I'm going to write this as a change in x, a final minus initial value, x minus x naught. Now, if this is the actual total force acting in the x direction, well, the component in the x direction, F sub x, we know we can apply Newton's second law, and we can write this then as the net force in the x direction is the mass times the acceleration in the x direction. So that's the total force in the x direction, the x component of F, times x minus x naught. Okay, there we go. So to go from here to here, all we have had to do is assume that our displacement was actually, the delta R was actually in the x direction, and the force that we're considering is the total force, the net force acting on the object. All right, very good. Now, let's look at this little piece right here. AX times x minus x naught. Hopefully that looks a little familiar to you. We have seen that combination of quantities before. AX times x minus x naught. Where have we seen that? Can you remember? It's actually in the fourth kinematic equation when we were looking at two-dimensional kinematic equations. It's the fourth x equation. In other words, it was, remember, v sub x squared equals v naught sub x squared plus 2ax x minus x naught. So this term is this part right there, a sub x times x minus x naught. Well, that's very interesting. Let's see if we can't separate that out and maybe use this idea of work in this equation. So how can we do that? Well, first, let's try to make it look like this thing. So we're going to divide off a 2. So what do we have? Divide this equation, both sides, by 2. And we have 1/2 vx squared equals 1/2 v naught x squared plus ax x minus x naught. Okay? Now, to make it look like this, we're going to multiply everything by an m. So I'm going to put an m here, I'm going to put an m here, and what do we have? We have 1/2 mvx squared equals 1/2 mv naught x squared plus ma sub x minus x naught. But that is exactly what we have here, which is the work done. There we go. Well, this is a very interesting result. Let's take a look at this just for a minute. What are these? We've got this work. Now we know what the work means, but what are these things over here? We've got 1/2 mvx squared, 1/2 mv naught x squared. Well, these look like the same term, except this one is evaluated finally, and this one is evaluated initially. They are both 1/2 mvx squared, but this is 1/2 mvx squared evaluated finally, and this is 1/2 mvx squared evaluated initially. In other words, 1/2 mv naught x squared. Well, we're going to define these things as a new quantity, and this is called the kinetic energy. Which we will write as K sub E, and sometimes just K for short. So what do we have here? We have a very, very interesting result. Let me erase this and put it down again and stick some numbers in. Let's take a look at it. From 1/2 mvx squared equals 1/2 v naught x squared plus the work done. This is the kinetic energy. Now, this is only motion. We only talked about motion in one dimension. What if it's moving in the x and y and z dimension, something like that? We'll generalize this in just a minute. But just for the time being, let's imagine we've only got motion in the x direction. So this is what we call the kinetic energy, the final kinetic energy, the initial kinetic energy plus the work done. Or, bringing k naught over to the other side, we have W equals K minus K naught, final minus initial, in other words, delta K. This is a very, very important result. This is called the work kinetic energy theorem. Couple places we're going to go from here. We're going to generalize this to motion in more than one direction, not just x, but x, y, and z. And also, I'm going to say something, an approximation, or an assumption, I should say, with the work done. But before we do that, let's look at a simple case, and then we'll generalize it a bit more. What does this mean, this kinetic energy? This is a new term. Kinetic, we know, like the kinematic equations, means motion. Kinetic energy means energy of motion. It's an energy that an object has if it's in motion. So let's stick some numbers in here. Let's imagine we have an object with, let's say, a mass of 4 kilograms, and let's imagine it's moving along at 5 meters per second. This object, because it's moving, has a certain amount of energy. Now, what is energy? Energy is kind of a nebulous quantity, and we're going to be talking about different kinds of energy. Objects can have different kinds of energy that we'll see as we develop some of these ideas. But the first kind of energy that we're going to talk about now is kinetic energy, energy of motion. One way of thinking of it is that an object has energy if it can do work. So if something can do work, it must have energy to do that work. Okay, so how much kinetic energy does this thing have? Well, the kinetic energy we know is 1/2 m Vx, but I'm going to generalize this, and actually I'm just going to write down V squared. We'll see how we can make that generalization in just a minute. But just let's assume that we can do that. 1/2 mv squared. And what do we get? 1/2 times the mass, 4 kilograms, times V, 5 meters per second, squared. And what do we get? 1/2 times 4 is 2, times 25, 50. So 50 kilogram meters per second squared, or meters squared per second squared. And what's a kilogram meter squared per second squared? It's a joule. So that is 50.0 joules, which is what we would expect, because if we've got an equation where the work is equal to a kinetic energy, we know these must be expressible in the same units. So if we stick in the standard SI units for mass and velocity, we should come out with a standard SI unit for kinetic energy or work, which we have said is joules. All right, very good. So let's just think about this. So an object in motion has kinetic energy. The greater the mass, the more kinetic energy it has. The faster it's going, the more kinetic energy it has. Okay? So an object moving has a certain amount of kinetic energy. All right, very good. Now, one assumption that we have made, let me write down our definition for work. Remember, work was equal to F delta R cos theta. The assumption here is that when we are solving for the work acting on something, we kind of made the assumption that the force, as it's moving the object, is constant. We are assuming we have a constant force. And this is what we get for the work done when we have a constant force. In other words, that's not changing. What happens if, while we're pulling our object, sometimes we pull lightly, sometimes we pull harder? What if during this displacement delta R, the force is not constant? What if it's changing? Well, let's take a look at that, because that's going to lead us to a more general form for our definition of work. Let's imagine that as we move our object along the displacement, so it starts out at some initial position, and we'll imagine all of this is still just one-dimensional. We'll generalize it to more than one dimension shortly. But let's imagine that it's going to move from some initial position x0 to some final position x, and during that motion, the force varies. Sometimes it's a small force, sometimes it's a larger force, and it changes. So let's imagine that we've got some relationship as our object moves from an initial position to the final position. Let's imagine that the force is varying some arbitrary way. So let's actually assume that we're looking at F sub x. We're looking at only the x component of the force. It could be a general direction. We'll generalize it even more in just a minute. So at some initial point x0, our force is here. So that's our initial force. And then at some final time here, our final force is some different value. And as we move it from x0 to x, the force changes. So how are we going to figure out what's the work done? Remember, the work in this case is F sub x times the displacement delta x. But that only works when the force is constant. How are we going to use this when the force is not constant? What we're going to do is divide up the displacement into small regions where the force doesn't vary very much, or at least it varies just slightly, that we can assume it's relatively constant over that interval. So what we're going to do is imagine breaking up our displacement here into small little distances of delta x. And I'll say delta x sub I, because we'll have delta x1, delta x2, delta x3, delta x4. We'll have as many little tiny delta x displacements as we need. So that over this small displacement delta x, we'll assume that the force is basically constant. If we have a very rapidly changing force, we'll have to divide the delta x into very, very small, tiny intervals. But if we've got a slowly varying force, maybe we can make it slightly larger displacements. So how much work is going to be done over each one of these? If we figure out how much work is done over each one of these little displacements, all we have to do is add up the total work to give us how much work was done over the entire motion. So how much work was done over this little displacement? Well, we've got delta x here, and the force up here. The little tiny work done, we'll call this delta w sub I. The small amount of work done over the ith displacement will be equal to, whatever that force is at that point, maybe we can call this F sub I, Fx sub I times delta xi, delta xi. So that will be the small amount of work done over that little displacement. And then we just find out how much work is done over every little tiny displacement and add them up. But before we do that, let's look at this for a second. What is Fxi times delta xi? Delta xi is the width of the little bottom of this little shape, which is basically a little rectangle. We're assuming that the force at the top is constant. So basically we're kind of assuming that it's basically not changing over that width, delta x. So F sub I is this length here. It's this length, F sub I. So what is F sub I times delta xi, or say F sub xi, times delta xi? It's basically the area of this rectangle. It's the length of the base times the length of the height, base times height. Now, these are not distances. They're not both distances. We've got one distance and one force. But if we think of this as a kind of more generalized rectangle, a rectangle not just in distance and distance, but distance and force, it's the area of that rectangle. And that is the small amount of work done. And if we add up all of those works, we're adding up the area of all of these little rectangles. And what are we going to get? We're getting the area of this whole thing under the curve. We're getting the entire area under the curve. Well, that sounds like an integral. Well, let's see where this comes from. If this is the small amount of work done, the total work done will be the sum of all of these little tiny works, which is then the sum of Fx sub I times delta xi. And this is an approximation, assuming that we take our little displacement small enough so that the force is constant over it. But if we want to try and do this exactly, we'll have to make our delta x's so small that the force really is constant over it. In other words, we have to make our delta x's infinitesimally small. And then rather than just summing up them, what do we have to do? We have to integrate. So this sum, then when we take our delta x's so small that we could call them dx, that sum becomes an integral. So the work is then the integral of f sub x dx. Still, remember, the component of the force in the x direction. And then we integrate from where to where? We integrate from our initial position, x naught, to our final position, x. Well, there we go. This is a very, very interesting result, and is much more general than what we started with up here. So this will work even for a varying force. We integrate fx dx from x naught to x, and that will tell us the work done over that motion from x naught to x. Great, let's stick some numbers in here.